So, let us see what we have finished till now. We have addressed the Dirichlet problem on open domain, and where boundary data is given, and then we would like to solve the Laplacian of u is equal to 0, that equation where boundary data is also given. So, for that we have seen that we can find out stochastic representation. That means that we can write down the solution of the problem as a conditional expectation of random variable. Okay, so let us summarize whatever we have done yet till now. This is the statement of the Dirichlet problem, that find a function u which is harmonic on the open domain D, okay, as well as continuous on the closure, okay, such that on the boundary del D is the boundary. So, on the boundary u satisfies the given condition, that function f, where f is a continuous function on the boundary. Okay. So, that is the Dirichlet problem. For this problem, what we have seen is that if f is bounded, okay, in addition to continuous, so continuous and bounded, and the probability that exit time is finite is 1, that means exit time is finite almost surely, then we can evaluate w tau d, because then this is meaningful, correct. If tau d is infinity with some positive probability, then this is w infinity, which makes no sense. So, we need of course this condition to write down w subscript tau d, that Brownian motion at time tau d. So, in this case we can, any bounded solution to the Dirichlet problem df is written as u of x is equal to expectation of f of w tau d given w 0 is equal to x. Okay. So, this is the result what we have seen earlier, but this does not imply that given any domain D and any bounded continuous function f, this function would be a solution of the given Dirichlet problem. It does not say that. It says the other way around. It says that if the Dirichlet problem has a bounded solution, okay, then that solution can be written this way. However, there could be an occasion that the Dirichlet problem does not have any bounded solution, it does not have any solution. Okay. So, then also this function may make sense. Why? Because this makes sense, because f is always bounded, so expectation is finite, and tau d is finite with probability 1. So, this makes sense. So, this function always makes sense. Okay. This function always exists. However, this is just a candidate solution therefore. Okay. So, this is a candidate for the solution. So this statement just says that, okay, if the Dirichlet problem has a bounded solution, then the solution can be written this way. This also says that the bounded solution is unique. Whenever we have this condition true, that this condition is purely depending on the structure of the domain, correct? It does not depend on the boundary data. So, if this condition is true, then the Dirichlet problem has only unique bounded solution. Okay. If the solution is there, then it is unique. Okay. It does not talk about existence, it talks about uniqueness. Okay. However, this result is although this result is interesting, but this result does not help us to answer to the question whether given Dirichlet problem has any solution or not. Okay. So, we have discussed that we have figured out that the scenarios when existence fails, that fails only when that the candidate solution is not continuous on the boundary. So, what we have done is that, so if A is in the boundary which satisfies Zaremba cone condition, this cone condition also depends purely on the nature of the domain. Okay. So, then this A point A is called regular, and additionally that means if you have all these conditions true, like f is bounded continuous and tau d is finite with probability 1, and also if every boundary point of D is regular, then this Dirichlet problem df has a unique bounded solution u. So, this is talking about existence. Okay. Then it has a unique bounded solution u, which is given by this conditional expectation. Okay. So, that is the final result for this type of for this discussion, correct. Given a PDE problem, we always try to find out one sufficient condition under which we can assure the existence of a solution, and then we also ask that, okay, if it exists, okay, whether there is a unique solution. Okay, so for existence is concerned, so we have a complete answer for the Dirichlet problem. Okay, so we have seen the proof of this result, and next the following result we have not proved, but let me state this, because that would then help us to have a complete picture about Dirichlet problem. We have so far talked about only the scenario where the exit time is finite with probability 1. One can ask that what happens that if I do not have this condition true. Okay. So, one would lose uniqueness. Okay. So, this is the precise statement here. If we consider a function v of x, which is defined as probability that tau d is equal to infinity, given w0 is equal to x. So, if this is non-zero, okay, if this is non-zero, that means tau d is infinite with some positive probability. So, then this would be a non-trivial function. Nevertheless, this function would still remain harmonic. Okay, is still harmonic. Okay. So, like here we had ux, correct, defined this way, that was harmonic function, correct, and this function is also harmonic function. This is a very nice result. And if A is a point on the boundary such that it is a regular point, then limit of Vx as x tends to A goes to 0. That is quite natural, because if you are close to boundary and then you are asking that, okay, the exit time is infinity, what is the probability? Of course, that probability should go to 0, because it is very likely that you would hit the boundary if it is very close to the boundary. Okay. However, if the point is an irregular point, we know that some examples like Leibniz Thorn. Okay. So, there even if you are very close to the boundary, but still the probability that you would exit in finite time might not decrease to 0, because it may live away. I mean, the kind of scope it can explore in the near here, there it might not touch the boundary and can go away. Okay. So, there might be a positive probability that exit time is infinite. Okay. So, for those cases, we cannot assure that this Vx would go to 0 as you are approaching to the boundary. Nevertheless, if A is regular, that means those kind of pathological scenarios are excluded, then you would have this result. Okay. So, this is also a theorem which I am not proving, I am just stating it. Next, if f is just bounded continuous function, okay, as before, however, like the point 8 is removed, the tau d finite, this condition is dropped, just f is bounded continuous is retained, and every boundary point of D is regular. Okay, that is also retained from earlier. Then this function u, which is defined as conditional expectation of f of w tau d, and indicate a function that tau d is finite. Okay, and this is actually generalization of the earlier one. Even if you put this thing earlier one, that will be exactly 1 almost surely, because tau d is finite almost surely. Okay, so this is just generalization of the earlier one. So, this is a bounded solution to DF. Okay. So, this is the extension of this thing, and this works. So, this is also a bounded solution to DF. But are there any other solutions to DF? Of course, from 12 we can see that of course there are many others. Why? Because so if tau d is infinite with some positive probability, that means V is non-trivial function. if V is non-trivial function and harmonic in D, that means it satisfies, is non-trivial function which satisfies the PD, okay, that Laplacian V is equal to 0. And here every point on the boundary is regular, that means that Vx converges to 0 on the boundary. So, this Vx itself satisfies the Dirichlet problem D comma 0. So, V satisfies a Dirichlet problem D comma 0, because on the boundary it is taking value 0. Then if I add V with U, okay, if I add V with, so U plus V, U is as before, so U satisfies this df and V satisfies d0. So, U plus V would satisfy df. Why? Because U plus V would still satisfy the PD, because the operator is linear, and on boundary condition V is adding nothing. So, you already had the f value and V has 0 value, so addition is f. And this also says that does not matter, you can actually take any multiple, any scalar, so U plus lambda V, lambda is any real number, okay. So, every bounded solution, so this is actually a reverse statement. So, from the discussion of 12 and 13 we can conclude U plus lambda V is also a solution of df for any lambda, and 14 is saying furthermore every bounded solution to df is of this form. If df has any bounded solution, it is of this form, okay. So, this much is like giving us a complete picture of Dirichlet problem, at least the bounded solution of Dirichlet problem, right. It is saying that, okay, the special case where exit time is finite, for those case the solution exists and it is unique, and it is given by the equation 10 that ux is equal to expectation of f is the boundary data of W is Brownian motion and tau d is the exit time, this way. And if one does not have this condition H, okay, that tau d finite, then also we can write down the solution, okay. We can assert existence of solution, but we cannot assert uniqueness. However, although we cannot assert uniqueness, but we can classify all the solution. In that case, we can write down all possible solutions, these are all this form, okay. So, this is complete answer of bounded solution of Dirichlet problem.